I will start with the intrinsically interpretable model and what is interpretability in general. Then I will tell you about two architectures that I really like, so the ProtoPNet and the PIPNet. Then I will talk a little bit about limitations and what are the research works related to them, and some things related to the interaction with the user. At the end, there is a paper about learning the interpretable model in a continual learning fashion, but we'll get there at the end. Each section is organized that way that at the beginning I'm showing the literature on which it is based. So starting with the interpretability, we have a definition that says that the model is interpretable when its behavior is predictable and understandable for the user. So we have two components, predictable and understandable. It means that we, as a users, understand the reasons behind the prediction, so we are able to predict the decision of the model based on the explanation. And as a user, we are also able to predict the explanation based on the classification of the model. And interpretability can be seen as a part of explainable AI or other way. So we saw yesterday from Wojciech Samek talk that there's a lot about XAI here, and there's like explosion of work in this field. So most of them, or the beginning of them, at the beginning they were mostly post hoc. So we are adding another model, which is called explainer, to our first black box neural network. And this is kind of problematic because this gives us biases or unreliable results. So here we have an example where we trained the model on NIST with true labels and random labels. And we can see that a lot of post hoc methods, which are attribution based, are not able to show the explanation for the random labels. So it should be noise, and we obtain something like edge detector or something similar. So they are mostly focusing on the object on the image, not on the explanation itself. So what if we can design a model, interpretable one? And this is a neural network, a deep neural network. So in that way, it's inherently interpretable. So within the prediction, we have the information about the explanation or the intuition behind the prediction. So to some extent, then, the model is faithful to what it does. So we have a direct, exact information from the model. And those models are also called anti-hoc or gray boxes, because we have some level of transparency. They are not fully transparent, obviously. And there is a discussion or dispute that the XAI and interpretability are not the same, because they have a little different origins. So interpretability is dated to 1950 because there are some models, beginning of the decision trees and other stuff, where people were discussing how many factors we should have in linear regression, for example, to understand how the linear regression model works. And if, do we agree with that or not? It depends, but we should be at least aware that there are some concepts already there, and we can somehow combine them for our means, also in the XAI. But in the center of it is the user. So he should or she should be able to understand and predict. So the models. I will speak only about two. There is the third one I really liked. It's called BCOS. So very simple name, but is written as beta minus cosinus. Which is attribution-based, and I'm focusing mostly on concept-based models, especially prototypical ones. So starting with the ProtoPNet, it has this idea that something looks like something. So in this case, we have our bird, and the parts of the bird are similar to the parts of the other birds from the training data set. And we can see the activation, so we can say that this is the sparrow because it's similar to its parts are similar to the other sparrows. And here is the architecture. So we take the input image, we push it through a convolutional backbone, and we obtain from ResNet, for example, a latent map, which is 7 by 7 by the number of channels. And each pixel 1 by 1 by the number of channel can be treated as a prototypical part, which is compared to a trainable parameter vector, which is the prototypical part, and then we take the maximum activation. So to visualize it differently, we obtain this feature map. We compare to a single prototype, which is encoding some part from the training dataset, but this part is trainable. So within the training process, we are trying to find this part from the training dataset. And then we obtain this similarity map, and at the end, for a single prototype, we take the maximum activation. So we know how much of the presence this prototypical part has on the image. And this information goes to the last layer, which is just a linear layer, without bias. The other one is a PIPNet. The beginning is the same. We end up with something by something, but the number of channels. And here, instead of comparing to some prototypical part, we are doing the softmax per pixel. So for each channel, we calculate its maximum activation in terms of softmax. So in that way, each channel represents the prototypical part. And then we can classify it based on the max pooling from the whole channels of the network. So what are the limitations, especially from the user perspective? Starting with the spatial misalignment, if we look at the feature map, we can see, similarity map, we can see where the prototypical part activates itself. And from our intuition, if we change the image outside this region where it's not activating, the placement and the strength of activation of this prototypical part should be preserved. So here we change the background behind the bird, and the activation from the neck went to the wing of the bird. But this is still the same prototypical part. So to translate, it means that the different pixels that are then they are showed by the similarity map were important for this prototypical part. So how we can measure that? We can define an adversarial modification outside the high activation region of the prototypical part and check if we can make it in that way that we will minimize the activation of the prototypical part. If so, it means that the pixels outside the high activation regions were important. And based on that, we can define metrics. For example, we can define how much it was, the translation was of the prototypical part. So how much does it move? Also, we can change how the activation changed, how the accuracy changed, and what is the order of the most influential prototypical parts on the image. The second part is that right now we can define a user study, show the users the explanations, and ask whether the user think that the model is correct. And it turns out that when the model is incorrect and the user sees the explanation, almost half of the time the user thinks that the model is correct. The explanations right now are making the user overconfident into the model. And this is a really serious problem because users are not thinking critically about the model's decision when seeing the explanations. And it's also confirmed for other models from like BACnet, but also GradCam and other ways. So this is a really important challenge to tackle. So we truly understand as a users and as a researchers in interpretable AI that the user needs to be engaged and needs to understand that it needs to be looking and judging the model's decision. Because when somebody explains something to us, we are believing. So we have this bias as humans to believe things that are justified by something. But how we can reduce it? So one way is to make better explanations. So instead of having this simple idea of this looks like that, so this wing looks like this wing, we can say this wing looks like those wings or those beaks. So we are showing more examples. so the user can grasp better the idea what lies behind a given prototypical parse. If they will be random, then probably it won't trust it. And how we can do it? We can define a prototype not only as a just a simple vector, but as a ball that contains multiple vectors. Can we do more? So with a recent paper, we did Lucid PPN, where we are also explaining the decision with few examples, but we are also dissecting color information from the shape and texture information. So we can see what really was important for the model. Because when looking at those explanations, we don't know if this is the color or maybe the contrast between the neck and the head. And the second contribution was that we fixed the placement of the given prototypical part. So we said that each bird should have a prototypical part of a head, of a neck, of a wing, and of legs. So how we can do such a thing? So firstly, we need to treat it as a multimodal approach. So we have two branches of the model. We have the shape tech net and the color net. Into the color net, we just push the downscaled input of the image. So we lose all the information about the details, high frequency details, while we use the grayscaled image as a shape and texture information. We push it through the models, and at the end we do the information fusion and so on and so forth. But besides that, on ShapeTechNet, we also enforce that if for a given data class we have assigned 4 prototypical parts, they are assigned to 4 different places, but consistently over all classes. And this can be done with, for example, a model called PediscoNet, which discovers object parts, and then based on the segmentation to that we can enforce for that. So here you can see the results on the left of the user study, that the Lucid is more interpretable, or people are less overconfident than the PipNet or the random. However, there is another bar called single branch. So this shows what really improved the overconfidence or make them less overconfident. And it was the information from PediscoNet. So from the model that was showing the different object parts to make them consistent between bird species. However, if we run this model on the cars dataset, we can see that adding information about color is not changing the classification accuracy. So it means that the color can be even a confounder. For some of the datasets, we also found that adding the color information reduces the accuracy. So next is the interaction with the user. And here I just want to mention one paper that they are using the concept-based models like ProtoPNet. And if they detect a confounder, they are able to unlearn it. So we have this information. We ask the user whether this is a confounder and not. And if 5 of the users will tell, yeah, this is a confounder, or 20% of them, then we can retrain the model to forget it. So not to use it into the classification performance, into the classification process. So this can be, as in this example, the prototypical part of a background. However, this is just forgetting. So we are reducing the capacity of the network, we are reducing the information that it's using. So maybe we can also put some positive information about data classes from the users to the model. That's the question to be answered. And then the continual learning. So here you have an example. If we take the interpretable model and we run most of the currently baselines for continual learning, we can see that the catastrophic forgetting can be also seen as the interpretability concept drift. So the information about the prototype is changing after learning another tasks. So the model is not representing the concept that learned initially the same way. And in some of the methods, it's even like showing all the image, so it's just random. So we can measure that thing by just taking the IOU between the concepts from task 1 to the same concepts preserved after learning next tasks. So how we can do so? I will only tell about one contribution, which is the interpretability regularization. So we take the activation of the frozen network after the task t-1, and we want to have the aligned maximum activation between the current model, which is learning on new examples, to have the activation of the old prototypes on this new example in the same places. And why we want to have it on the maximum value? Because maximum value is the most important. So let's start with the plot at the bottom. This is the function of similarity in terms of the distance. So as I said, in proto-pinot we calculate the distance, which is transformed to similarity. So if the distance is small, it's very important for the model. If the distance is large, like 2 or 5, it doesn't matter. It's useless. So we can use the model that we have already to accommodate new knowledge by just enforcing it to learn it within the places where the distance is large. So by using the similarity value, which is shown on the plot on the right, in the top panel, that if something is close, it means that this is a valuable information. If something is distant, we can forget it and learn a new concept. So here you can see the results in terms of the interpretability concept drift metric, and our model is the best in terms of this metric. So the concepts are preserved, and they are preserved much better than all the others. Yeah. So I've missed one slide. I also invite you to the talks to other people from GMUM. Przemek will be here soon, so he will show that. And I think that this is concluding my talk. Thank you.